So if you have started the network models lecture materials, now you can actually try to solve the exercise problems in these documents. In this video, I try to explain how to model and solve the problems. The first exercise is a transportation problem. So on this slide, you can see the necessary information for the problem. So now let's try to formulate this problem first. First, let's try to go through the parameters and draw a network. So in this exercise, start from the structure of the network. So suppose we have 3 factories and 3 markets. So then we use F1 to represent the factory 1, factory 2, factory 3, and use capital M to represent the markets. Then you have M1, M2, M3, M4, and M5. So the 3 factories can produce goods and send the goods to the markets. So there is no limitations about which factory to serve which market. So we suppose or assume factory 1 can provide products to all the markets. Then you can actually draw the routes or the axes from factory 1 to all the markets. So similarly for F2 and F3, so we just try to draw all the axes. So this is a system network. Now let's see the parameters. So in factories, we know the supply. So for example, just write supply. So in the question, they actually said denote supply as AI. So we can write here AI. I is the index for the factories equals to 1, 2, 3. Then we have the factory 1's supply capacity 100 units, factory 2 150, factory 3 250. We also know the demand in each market, so we use a BJ to represent the demand from each market. Then we have 50 units in the market 1, 70 units demand for M2, then the rest of them also given. So this is a demand, so this is a supply, so this is demand. Furthermore, we also know the transportation costs from about each route. So in the table we got these parameters. So if we want to formulate this problem, we need to next step define the decision variables. So the question is to decide how many units to provide the products from one factory to one market. So here we define the decision variable x Ig as the units or the quantity of products transported from factory I to market G. So here we know I and G are the index for the factories and the markets. So in I equals 1, 2, 3, G equals to 1, 2, 3, 4, 5. Then next step, we construct the projective function. This is actually, as we have done many times in the other exercise, so we're interested in minimize the total costs. For example, you can use a letter zeta to represent the total costs. So we know the unit transportation cost from one location I to one location J, and if you also know the transportation quantity, so that's actually is the cost for each route. Then now we have multiple routes, so for all the markets, for all the factories routes, so that's how we calculate the total cost. So I do not have space to write the constraints, so I just shrink everything I have done so far, so just find some space. So now the fourth step, we try to define the constraints. So the constraints actually mainly two types. So you can try to identify the constraints from two directions. One, we can think about the outflows or the flow out and flow in. So in the supply side, then there are flow out. So in the market side, there's a flow in. So in the supply side, now you can see you have the each supply set or each factory, the total supply is a sigma G for all the markets and Xig. So this actually is a total supply for the factory I, and the capacity for each factory is AI. So we know AI equals to 150 and 250. So this is the supply constraints. If you think about this as the flow out, like the textbook has done, you actually can add a minus sign. So this actually is the equivalent constraints. You can just write the simple form, or you can also show the flow out sign. So the flow in, you just need to sum up the total products arrived in each market. So you sum up the providings from each factory, and this should be equals to, this is a demand BG. So the BG is the demand. So if you elaborate all these constraints, then it's related to each market. So you write here, it should be for 3 factories, and the second constraint should be 5 markets. So you have 3 supply constraints and 5 demand constraints. So I do not write the individual constraints here. So if you want to see what happened, so check the Excel settings and you see all these constraints actually calculated. So of course, we also have a non-negativity constraints. So if we see this is one type, this is one type, this is third type. So this is the model. So furthermore, we can see in this problem, so the total supply from the three factories is so this is right. Total supply equals to sigma for the three factories. So this is 500 units, and the total demand. So BG is also 500. So we actually have a total supply equals to total demand. So this model is called a balanced model. So that's also why you can check directly write the constraints as an equivalent. This is about the first exercise. So after we got this model, we would like to actually solve this problem in Excel. So now you can see I just copied the Excel workbook layout here. There are two ways to actually solve this problem in Excel. So you can directly write all the decision variables in the row. So here you actually can see you have all the decision variables clearly stated as a row. Then each constraint related to individual decision variables you have to identify. For example, this is the supply constraints for the first factory. So this is F1, then F2, F3. So these are the supply constraints, and the rest of 5, these are the demand constraints. This is definitely fun. You can make such a layout. Just remember, use the constraint coefficient y, 1 to and 0 to identify the decision variables involved in each constraint. So that's also we call it layout 1. No. So this is a layout 1 corresponding to the Excel solution, the transportation problem 1 in the Excel transportation problem 1 in Excel workbook. Of course, we also have the alternative layout for the first problem. So now you can see the structure is a little bit simpler. So if we consider the decision variables as so here in this layout, the decision variables are defined or set as a matrix. So these are the decision variables. So just connect it. So these are the decision variables. Then this personally, I like this layout because it looks like a network structure. You can clearly see so XIG. So these are the factories, and these are the markets. And the cross cell for example, from factory 1 to market 1, your decision is to provide 50 units. So it's relatively easy to actually interpret your results in the end. So this is another option you could do. So we call it layout 2, or in the Excel workbook, it's called transportation problem 2. You can also try to solve it or find the solutions there. So we have mentioned before, so we know the problem initially is a balanced model. So the total supply equals to total demand. So here the question, one extra question is what happens if supply is strictly less than demand. So this formula means the total supply actually is less than total demand. So, for example, previously we have 500 units for the supply. If the market is good, so the demand increase to 550, what should you do? So you actually can change the constraints. So I just try to see where you should change. So in this case, so the total demand cannot be completely satisfied, and your supply are actually same. So you keep your supply constraints. So nothing changed in the supply constraints. You still have the sigma G in the multiple markets. Xig equals to your supply constraints. So this is for the 3 factory, and the demand constraint should be modified. So in this case now you cannot satisfy all the demands, so we try to actually satisfy part of the demand according to your supply. So you just change the demand for each set less than or equals to BG. So this actually is also explained in the lecture materials. So you just remember why this should be changed. Next question is what can we do if supply is strictly greater than demand? So here the total supply actually is greater than total demand. So in this case, you just make sure all the demands are satisfied. Of course, there are extra supply remain unused. So the supply constraint should be changed. So the total markets for each factory actually should be less than or equals to the supply. Of course, if you use a flow out constraint, then it should be Xg sum up over markets greater than minus AI. So this actually is also equivalent constraints. And then the demand constraints unchanged. So you satisfy all the demands in the markets. So if you understand what's happening, then that's fine. You can easily modify your model. So you can give an example, try to solve the problem yourself. For example, if the supply, the capacity for one factory increased, for example, for the A1, the capacity increased up to 150. What should you do? The second problem we would like to address is the transshipment problem. So this exercise actually is an extension from the previous exercise. So all the parameters from the exercise 1 still applied in this exercise. So we just briefly go through the information here. So suppose we have a transportation problem as before with 3 factories and 5 markets. Suppose further we have transshipment nodes in the network. So actually, apart from the factories and the markets, we also add the physical locations called transportation nodes. So here the transportation nodes have no supply, no demand. You just think about them as an intermediate hub or storage facilities. So now we need to find a minimum cost solution that sends the goods from the factories through the transshipment nodes to the markets. So the capacity on the factories are respected. Demand and the markets are met, so the previous parameters are still applied here. So if we send something from a transshipment node, it must initially be sent to the transshipment node from the factories. So this is known as inflow equals to outflow or flow balancing and constraints. Since the transshipment nodes involved in this problem, now you can see the cost information actually different from the previous. So we have the transportation costs from factory to the transshipment facility. If we use CI key to express, so this part is CI key, and from transshipment facility to the markets, then we have here further information, transportation information. So in order to distinguish with CI key, so I use a CKG prime. So that's a transportation cost. All the empty sizes not defined or not existed. So given the current information, we try to formulate this problem. First, let's see. So the parameters can be identified. We first draw the network. So we have 3 factories as before, 5 markets, and we have 2 transshipment facility. So now the transportation routes, sorry, I change our color. So the transportation route is defined from factory to the transshipment sets. And also from the transshipment to all the markets. And then we know the supply. So AI given. So this is 100, 150, 250, and we know the demand. So here is a 50, 75, 125, 150, 100. still this is a balanced problem. We have the total supply equals to total demand. So we know the cost information. So next step, we try to define the decision variables. So next step, we try to define decision variables. I start from the more intuitive method. So we define the routes from the factories to the transportation side as X, I key, and in the from the transportation set to the markets as a Y key G. In this case, we need to actually define index. So we use I to further represent the factories and G to represent the markets. And then we use key to represent the transshipment nodes. Then next step, we define X, I key is the units of products transported from factory I to transshipment node key, and we know I key, and we define another decision variable Y key G and the units of products transported from transshipment place to markets G. So again, we have key equals to 1 to 2, G equals to 1 to 5. So these are the decision variables. So next step, we define objective function. So we know the cost information here, so we just minimize the total costs. So here mainly two types of costs. So from factory to transshipment, from transshipment nodes to the markets. So we have the sigma total cost from the factories to the transshipment cost. Sorry. So C I key times X I key. And then we know that we're interested in total cost from transshipment node to the markets. So we have sigma key, sigma G, C prime, key G, Y key G. So this is the objective function. Of course, you should be able to extend all these matrix form constraints into the Excel setting up. So after we find all these decision variables, objective functions, the next step, we try to construct the constraints. So apart from the supply constraints and the demand constraints, and we need the transshipment balance constraints. So the supply constraint we have done before, so it's a total for each factory, so the total outflow or the flow out quantity xi key should equals to the capacity for each factory, and for the demand side, so the total demand sets, so it's a mistake. So the demand constraint is the total flow out from each transshipment node to the markets. So we have a kg, ykg, sum up equals to bg. Of course, you need to write index definition. And the transshipment constant is new here. So the idea is move them here. So the idea for the transshipment constant is flow out from this node equals to flow in. So the flow in actually is a total supply from factories. So x I k sum up from all the factories equals to the flow out for all the markets. So for each transshipment nodes, they should be balanced. Then of course it's related to I equals to 1, 2, 3, j equals to 3, 4, 5. So that's the transshipment constraint, and plus the last constraint is the non-negative constraint. Then you have a completed mathematical model for this exercise. I do not explain how can you actually realize this model in the Excel solver. I provide a student template already. You probably already tried to solve that. So here we just directly see the possible layout you can choose for to solve these problems. So this here I show you the first layout. So I provide two layouts, but they give exactly same solution. That's just different way you can make a Excel setting up for the transshipment problem. So the first layout you can see we use the decision variable x ig and yig. So here actually it doesn't matter you use ig or I key. I particularly use I key because I try to use different index. So here if you wish you could change the yig into ykg, because now you can see this actually means from transportation transshipment place to the markets. And from this layout, you can see the decision variables are two parts. So we have the first part, decision variable, and then we have a second part, decision variable, and then the rest of them you should be able to figure out how to realize the constraints and solve the problem. The second layout actually is your option if you're interested in trying it, because the textbook has also used this layout. I just give you the solution. I do not clarify the formulas, but now you can see I only defined a single type of decision variables xig, so you can clearly see the transshipment points actually become a part of your flow out point. And at the same time, transshipment points are also the flow in locations. So you just extend the matrix. So here is a flow out set. So here you have a flow ins. Then try to define the decision variables. You have decision variables here, two submatrix here. If we use that here and here, these are the decision variables. Basically, there's no difference from the previous model. That's just how you actually solve the problem in Excel or realize the solver layout. The rest of the parts are also same, so you can easily figure out the supply constraints and demand constraints. And here we have a transshipment constraints. You have the Excel solution as well. Try to figure out. So in the textbook, there is something very special. They actually use a very large artificial costs to avoid this root defined. So here we didn't use that because the adjustable or decision variables are only specified in the yellow sections. So all these empty cells are not defined as the decision variables, so that will not affect your solution. You can just keep them empty.